All right, so the first thing we're going to take a look at is some more melting points. And so like last time, we could do simple melting points. However, some compounds don't do so well with that. And so if you take an organic compound, put it in the presence of oxygen, and then add some heat, so this triangle is heat, you may or may not get a reaction. So some compounds simply aren't stable in atmospheric conditions, right? With all this oxygen floating around. And so if you try to do a regular open melting point, you might get a reaction with your compound and you might get decomposition. And so you're not taking its real melting point. The other thing that can happen is some compounds sublime. So maybe your compound sublimes before you really get a good melting point. And so to solve this issue, we can do what's called an evacuated melting point. So what we do here is we have our Pasteur pipette, right? Here's a pretty terrible drawing in it. This is a pipette, not a paddle. Anyways, you put some small amount of material down here. Getting the 2 millimeters is going to be a lot more difficult because it's harder to get it down in there and get exactly 2 millimeters. You connect this part up to a vacuum, and then you suck all the air out of it, right? That way there's no more oxygen here to react with. And then you simply create a seal and then a second seal down here to seal away your compound. And so now we have no oxygen. There's no reaction. And then, so that's one key thing. And then the other key thing, that it's sealed. And so your sample can't kind of escape away. And what we mean by escape away here is sublime away, right? Become a gas without turning into a liquid. Depending on how fast you heat it, it may or may not sublime away. You can see in this video, we actually don't see too much sublimation. You do see some sublimation, and we get a melting point. You can technically read the melting point on the first video, but you can see it'll be a lot different than our evacuated melting point. And so the evacuated melting point is going to give you kind of the real melting point here. Another thing that we want to remember is that we don't want to reuse melting point samples. And so we'll see you an example of this. And that's because these things can react and decompose at elevated temperatures. And so when you put them up at these elevated temperatures, they react. And then when you let them cool back down and you try to get another melting point, you're not really sure what you're taking the melting point of. It might still be your compound. Maybe it didn't decompose, but maybe it didn't, or maybe it did. And so you always want to use a fresh melting point sample. All right, so first thing we're going to do is find the melting point of our compound. So we've got it right here. Poured out some in a secondary container. It's already a powder, so we don't have to worry about grinding it up. I'll just take the open end of my capillary and then just dab it on the powder just to pick some up. Invert it and then just tap it down and get it nice and packed. And this should be plenty for our melting point. You can see that around the melting point range, we're going nice and slow. And as you can see, we are done. Next up, we're just going to repeat the same procedure, except this time with caffeine. So pack up my capillary, and ready to get started. All right, next up we're going to repeat the procedure with caffeine, which has a very high melting point, so we'll start heating it up very quickly. Lower down the heat when we get close. And you can see that our sample is actually gone before we could measure its melting point. All right, so as we saw with our last sample, it evaporated or it sublimed away, and so what we need to do is do an evacuated melting point. So we need to make our own capillary. We'll make it out of one of these long test tubes. So first up, we'll turn on our flame. And then we're just going to melt this open end shut. So we'll just stick it in the flame, rotate it a little bit, until we have a nice shut end on one side. After this, we're going to load our sample. So we've got our caffeine here. And then basically you're just going to put it into the top here and then just tap it down to the bottom. So we've got a little scupula here. You really don't need a whole lot of sample, just a small amount. And then just tap it down until you've got about 2 millimeters of sample in there. This looks good. All right, so what I have here is a trap, and it's attached to my vacuum, so I can turn on the vacuum. And then if anything gets sucked up
through the end of the vacuum, it'll get in the trap instead of actually going through the vacuum. So I'm going to attach my sample to this vacuum, and then I'm going to go ahead and close the vacuum here. And I'm going to allow my sample to get vacuum or evacuated for about 30 seconds. Alright, so our sample is still connected to the vacuum, and the vacuum is indeed still on. So all we're going to do now is point the flame up here and then seal this sample shut. And now we have our evacuated melting point capillary. All right, next up, I'm going to close up this pipette about 10 to 15 millimeters away. That way my sample doesn't have any place to sublime away to. So I'll hold the sample end with some forceps because it's going to go pretty close to the flame, and then I'll hold the other end with my finger, and then I'll dip this into the flame and I'll twist with this finger to seal it shut. And you can see it's all nice and twisted up and sealed shut. All right, we can see our caffeine's melted at this point. Just lower down the heat on our melt temp and let the melt temp cool back down. Let the caffeine recrystallize, and then we can get another reading. All right, so our sample has re-solidified. However, if you look at it, it looks a little bit different, and that's because it's just more crystalline. So in the middle is our sample that we used last time, and then on the far right is another sample that I prepared, so we can compare and contrast the two. As you can see, I lowered the heat too quickly, and so now we're kind of stuck here a little bit. I've increased the heat, so it should start, the temperature should start rising again, and we should see our compound melt. Cool, and both compounds have melted.
Next up, we'll take a look at a melting point of some mixtures. And so when you're thinking of a mixture, there should be kind of a major component and a minor component. And so you can think of the major component as the solvent and the minor component as the solute. And so your melting point should be closer to the solvent, right, to the major component. However, remember from Gen Chem that impurities, which in this case will be our solute, will both lower and broaden the melting point range, right? So something that's very impure or a mixture should have a lower and a broader melting point. There's a bit of camera error on pretty much all of these. My camera was stopping for some reason, and so these clips are going to end before they should. You'll notice that all the compound isn't fully melted. You can still get like an approximate melting point. Just make sure to write down the error in your lab manual. And so we'll do some of these mixtures of stuff, and then we'll do some unknowns, right? I'll show you two unknowns, show you the melting points, and you should be able to identify the compounds based on the melting point. And then after this, we'll do some boiling point of some compounds. This is the same as before from our practice, so there's nothing really new to say here. And then we'll do density as well, and this is the same as well. So nothing really to say about these two components of the lab.
All right, so next up we're going to find the boiling point of some heptane. So I've got my capillaries over here. I've got the heptane in a secondary container here, and then I've got some bells that I made last time here. So what we're going to do is fill these capillaries up with some heptane. Remember, we just want a tiny, tiny amount of heptane in here. So we got a little bit of heptane in there, and then we'll go ahead and insert one of our bells with the open side down. Here's one of our little bells. Go ahead, insert it into there, and then push it down if needed. And then I'll go ahead and make 2 more of these. That way we can run 3 of them at the same time in case something happens. Hopefully one will work well.
All right, so some ways we can identify compounds are based on their melting point, their boiling point, their density. Another thing we can take a look at is the refractive index. And so the idea behind refractive index is that light bends at the interface of 2 mediums, right? If you have 2 different things, 2 different surfaces, when light goes through it, it'll bend, right? So if this is the kind of separation between your first and second surface, if you've got a piece of light coming in here, it will bend, and then they'll have different angles, right? This angle and this angle are not the same thing. The most popular example of this is kind of dipping your hand or really anything in water. So you've probably noticed this before. If you try to take your hand, right, and dip it in some water, the light is going to refract, and so it doesn't look like your hand kind of matches up with your arm, right? Or if you're trying to catch a fish, right, it's not going to be exact. And so we can use this property. So we can use the refractive index, or basically how it refracts light of a material, to identify it. Right, same thing as melting point, boiling point, density. Different compounds will have different values for this, and so we can use this to identify them. And so what we're going to use here is called a refractometer. Right, good name, explains what it does. It measures the refractive index of a material. This is actually used a lot. A lot of people like beer brewing or wine brewing, they use it to measure how much alcohol their brew is. So it is pretty useful. We're going to use a more advanced one than they use, and it's pretty cool. So the first thing we're going to do is we're going to load the sample. And you'll see how to do this in the video. And then the second thing we're going to do is we're going to measure. And so basically what you're going to do is you're going to look in the eye hole. And then you're going to turn a knob. And you're going to turn this knob to align the horizon. Right, there's going to be like a little kind of horizon. That's how I would describe it. And you're going to want to align it. So let's see what that looks like. So here's just 3 different images of what this might look like. You may not see this kind of black bottom at all in the beginning, right? This black bottom area. You may not see that. You just need to keep turning the knob until you see it. And so you can see that there's this kind of X right here. And so what you want to do is you want that X to be aligned with this horizon, right? So this horizon needs to be lifted up. You can see this horizon is actually too high down, and then this one is just right. So the one on the right is one you want to end up with. And so that's you measuring the refractive index of your compound. And so once you have that locked into place, what you do is you just simply flip a switch. And then there's a kind of, you can think of it as a ruler behind it that measures this. And so you're going to read the numerical value on this ruler. So here's just an example of that. This is not the one from this video. So definitely, you know, don't think that this is the correct answer for the lab stuff. So let's learn how to read this. The first thing you're going to do is you're just going to totally ignore all this stuff on the bottom. This is a different scale. It's used for some other things, but we're not going to use it. So we're only going to focus on the top half of this thing, right? And so you got to read this correctly. So let's see how we're going to read this correctly. We see this is 1.490. This is 1.50. So we went up 0.01, right? So since our line, and the line that I'm talking about is this vertical line coming down here, since it's before the 150, we know that this is going to be numerically be 1.49. Right, 1.49 something, and now we can read it a little bit more exact, right? So here's 1.490, here's 1.50, and then there's some taller hash marks and some smaller hash marks. These taller hash marks, 1, 2, 3, 4. This one is also 1, 5, 6, 7, 8, 9, 10, or 9, and then this one would be number 10, right? So you can see it's divided up into 10 different spots. So if we were thinking about right over here, this would be 1.491. This would be 1.492, right? So we can see it's between somewhere 1.491 and 1.492. And so here's another kind of little tricky thing. This one actually has these little half marks as well, these half hash marks, right? So this is right in between these two values. So this would be 1.4915, right? Somewhere right in between these two values. And so we can see that it's less than 1.4915, but greater than 1.491. And it's somewhere right in between these two. And so the way you would read this number is 1.49125, right? We can see it's above this number right here, but it's below this number right here. And so if you think about what's right in between them, it'll be 125. Now, we have to think about this value. It's a little bit complicated because these half hash marks aren't based on a power of 10. Sig figs don't really work here. If you just wrote this number out like this, you would indicate that this is your uncertain digit, which you don't have this level of precision. This fourth decimal place or this fifth sig fig is actually your uncertain digit, right? If you think about it, we know this is definitely a 1. We know this is definitely a 2, and we know this is a 1.5, but it's somewhere in between these two numbers, between this one and between this one. And so sig figs don't really work out well here. So what you're going to want to do is just write out the number like this, and then you're going to want to include a plus or minus. In this case, our plus or minus is going to be 0.00025, or half the amount of our most precise calibration mark. And so that's just a little weird. So sig figs don't always work out that great, but if you have this plus or minus, you indicate that this too is really where your kind of uncertain digit is. So just do some practice. If you have some questions, contact your instructor. But you definitely want to be reading these correctly. And then once you have this numerical value, you're not done yet. You need to do a temperature correction. And you're going to do this temperature correction on your literature value. So when you look up these refractive indexes, wherever you find this refractive index, chances are you're going to get some symbol that looks like this, ND20. The N just stands for refractive index. The D means that it's coming from the sodium D line. Don't really worry about that. It's just coming from a sodium line. And this just tells you the wavelength of the light that's being used. And so in this case, it's 589.29 nanometers. Don't worry about that. These two are both very standard. And so is this last part. Most of these in the literature are going to be recorded at 20 degrees Celsius. At 20 degrees Celsius. So ours isn't temperature controlled. So our refractometer is not temperature controlled. And so it's going to read the refractive index at whatever temperature the room is at. And so that can vary. And so what we need to do is we need to take our literature value and do a correction. Because we don't expect it to be the literature value at 20 degrees if we're at 30 degrees or something like that. And so for most organic compounds, it's pretty simple. We're going to say that the refractive index changes the same according to temperature, and that's true for the most part. So our actual refractive index is going to be this NDX, right, where X is whatever temperature at. And so you're going to take your ND20, right? This is the number that you've Googled. You're going to say plus 20 degrees Celsius minus X degrees Celsius. So this temperature is whatever you're reading at, you know, whether the room's 22, 23, 24. And then you're going to multiply this difference by 0.0045, right? So for every degree, the refractive index should change 0.00045. And if you look at the math here, what this tells you, as the temperature increases, the refractive index decreases, right? So we have this one, right? If you're above room temperature, if you're above 20, this whole thing's going to be a negative, and then you're going to subtract out this 0.00045, right? So for every degree we're above 20 degrees, you subtract 0.00045. And then this will be your actual kind of literature value that you want to compare to. This is what you would actually expect your experimental data to match. And so you always want to write your experimentally found number, right? Whatever number the instrument told you, the literature value at 20 degrees Celsius, and then the corrected literature value. And you want to show your work for how you did this, right? That way, whoever's picking up this lab manual says, oh, where the heck did they get this value? I'm Googling it and I don't see this value. They can see how you got that value, right? You did a correction and they can see what correction you did, because it might not be standard for every single compound. And that's pretty much it for refractive index. All right, so here we have our refractometer. Here we're going to put in the sample, so we'll go ahead and open this up. And then we're going to put a small piece of filter paper right into the sample holder. So right there. And then we're just going to put a little bit of our compound of interest. In this case, it is methanol. So just try to add a small amount, not too much. That should be plenty. Go ahead, close the refractometer. Move the light up to the refractometer. And then on the left here, there's a switch here to turn on the light. You want your light on.
And then what you're going to do is you're going to look through this hole and adjust this knob. And what you want to see is basically kind of like a sunset horizon. It's going to be very hard for me to get this on video, so I'll just show you a picture of it. Maybe I can. That's going to be really hard to get a video. You're going to use this knob to find the horizon, and then you're going to turn your light off. And then you'll read a numerical value from here when the light is off. You can see the numerical value there. And basically that's how you're going to do it.